All right, guys. Section 3.1, we're going to be talking about functions and all kinds of stuff about functions today. The first thing we're going to talk about is before something can be called a function, it's a relation. And a relation is just a simple correspondence between two sets. And the two sets we normally are going to deal with are domain and range. And in algebra class, domain usually refers to which letter? You may remember. It's X, yeah. Domain's X, that would mean range would be Y. So the domain are the X values, the range are the Y values. You might also see that called the input and output. Sometimes you see that see input and output used in a place of domain and range. It's the same thing. Domain and range, X's and Y values. That's the two sets we're going to talk about the correspondence between when we talk about functions and relations in this particular class. So an example of a relation in a set form using curly braces. So to make those curly braces, curl down, put a little point in the middle, and curl down on the bottom. That's a curly brace. Don't just make a little squiggly. That's not a curly brace. Be picky. There's an ordered pair. There's an ordered pair. There's an ordered pair. Three ordered pairs in that relation. X values, Y values. X always comes first. Don't forget that. X, Y. On those. So the domain would be all the X values. The range would be all the Y values out of that. So there's an example of a relation. It's just a correspondence. The correspondence we're dealing with is domain and range with X's and Y values, normally in an ordered pair type format is what we're dealing with. Hey. Okay. All right. And then let's get a definition of a function. A function from X to Y. There are functions that go the other direction. All the ones we're going to deal with in this course are from X to Y. So the X is the domain, the Y is the range. If you swap that, it swaps the domain and range, and it's a slightly different set of rules. It associates each X with one Y. Doesn't repeat X's. Okay. If you're a function, you don't repeat your X's. Okay. If a relation is a function, the X values do not repeat. Y values are okay to repeat. You could have a relation that has, different X values and everybody has the same Y value of 3. That's okay, as long as the X values don't repeat. Functions don't repeat X's. They can repeat Y's, but do not repeat X's. Okay, so that's kind of the test you're looking at here is, does it repeat X values? If we're going to decide if a relation is a function, we look at the X values. If it repeats, it's not a function. If it doesn't repeat, it is a function. That's by definition. That's what a function is. Okay, so we're going to play the game. Is the relation a function? Example A. There's a relation 2, 3. It's the first ordered pair. -3, 5. 6, 4. 8, -2. So expressing this relation in a set of ordered pairs, the various ways that we can express a relation. We want to decide, is this relation a function? So what do we look for? Repeated x's. Are there any x values that are repeated? No. So this, yes, it is a function. -3, 7, 8, -1, -2, 7, 8, 0. Is that relation, again in a set of ordered pairs, is it a function? Why not? Repeated x values. 8 and 8 repeats there. So the reason behind it not being a function is that it has a repeated x value. Okay, so if it's not a function, you've got to tell me why. Why is it not a function? Because it's got a repeated x value. Another way that relations could be presented to you is a mapping. And that's where you have these bubbles. One is a domain bubble, one's the range bubble. And what they do is they just map the x values that are in the domain bubble to the range values by just drawing arrows. And so these would be already drawn for you. And this is how the problem would be presented to you. And they're saying, okay, is this a function? This relation represented as a mapping. So repeated x value? No. So it is a function. Because it doesn't repeat x values. It repeats a y value, but that's legal. You can do that. Okay, that's not a problem. Do another bubble. Domain, range, I'll just abbreviate D and R. 3, -5, 8, 7, -9, 10, and 3 to 7, 5 to -9, 8 to 10, and 3 to 10. Is that a function? No. You got a repeated x value right there. The 3, that's what was repeated, so we can't have that being a function. Okay. All right. Now, they could also represent a relation as an equation. 3x minus 2. Pretty simple equation. What do we know about that equation? What kind? What form, maybe? It's in slope-intercept form, which we know makes what kind of picture? A line, right? Straight line, okay, of some sort. We know, just sketching the graph here, I'm not really trying to be just too precise. We know that the y-intercept is where for this one? -2, so it'd be somewhere down there. And then the slope is +3, so that's up and over, right? Up and to the right. So we know it looks something like that. Don't have to have the perfect graph there. We just got to have an idea what it looks like. Now, what do we know that this line represents? Or do we know it represents anything? The line doesn't represent slope. The line has slope, but it doesn't represent slope. It represents the equation, but what from the equation? The x and y values. Yeah, all the values, all those ordered pairs that make up that relation. Okay? And then what would make it a function, or what would make it not a function? It would be repeating x values, right? Okay, so how are we going to decide if they're repeating x values? Could we check every x value on this graph? Does that seem like an efficient method of doing things? No, absolutely not. That's a horrible idea. Because we had to check every x value. The arrows mean that this thing has more x values down here, and it's got a ton more up there. We never get none, right? That's kind of what I'm saying here. So, is there a test to decide if a graph is a function that you maybe have learned in Algebra 1? It's the vertical line test is the one. If we lay a vertical line anywhere on that graph, does it touch it in more than one place? Each time, this one only touches in one spot, this one only touches in one spot. I can't find a place on this graph where that line touches it twice. So it doesn't repeat x values. If it touched it twice, it fails. Okay, so this is a function because it passes the vertical line test. Anytime you've got an equation like this, the test, graph it and then try it with the vertical line test. Okay, that's always a good option. Graphing's one of the best things you can do. Anytime, if you don't know what else to do, graph it. A lot of times that helps. This one's a little different. Y squared equals x squared minus 4. Weird looking problem because it's got the y squared as well. Now I'll kind of help you out here with this one. If we were going to graph that, what do we need to do? Get y to be plain y, right? That makes things easier. So I would take the square root of both sides. And there's y. But this is plus or minus the square root of x squared minus 4. Okay? So when if I were to graph that, what happens here is I have a positive side of x squared minus 4 and a negative side of that. It actually looks like this. That's the positive side. Here's the negative side. It's a sideways parabola. That's what that ends up being. Would that pass the vertical line test? No, because we can drop that vertical line right there and get it to touch two places. There's two intersections with the vertical line, so this is not a function. Kind of the shortcut to that is to know that if both variables are squared, it's not a function. Okay? If both variables are squared, it's not a function. That's always the kind of the shortcut to that. All right. Now let's talk about some things. We've decided when things are functions or not. No repeating x values if it's a relation. If it's an equation, we can look at the graph and do the vertical line test. Once we've decided if something is a function, then that opens us up to being able to use function notation, which you've seen before. Function notation is that f of x thing. You have f of x is equal to 3x plus 5, something like that. We'll call this example G, I think is what we're on. What's f of x the same thing as? It's the same thing as y. F of x and y are the same thing. What this is just a little bit more descriptive way of writing y. It's saying y when x is a certain value. Okay, so if you're trying to find a function value, so they ask us to find f of -5. All that means to do is take -5 and put it in the place of x. That's all they're asking us to do. F of -5 means everywhere there's an x, put a -5. And then use order of operations to work that out. 3 times -5, -15, plus 5, -10. So f of -5 is equal to -10. What that creates is an ordered pair. What's the ordered pair that goes with that? -5, -10. Okay. Tie those ideas together. Function value creates ordered pairs. Ordered pairs can be useful in function value as well. Okay. Now, where they get a little more college algebra level, this is very much algebra 1 level. Where we get a little higher with this is when they give us this function, f of x is equal to 2x squared minus 3x, and they say find f of 2x. Being kind of smart. Saying, okay, I'm not going to give you something that's that easy. I'm going to give you something with a variable still in it. What does that mean we do with 2x? What do we replace with 2x? Replace x with 2x. Everywhere there's an x, you put a 2x. And then you use order of operations to work that out. So order of operations says parentheses first. Well, we put some parentheses in there just to separate it. And then it says exponents. Well, so the exponents on the 2x. 2x times 2x would be 4x squared. And then the next step would be multiplication and division left to right. So multiplication 2 times 4x squared is 8x squared. And then 3 times 2 is 6x. So there's f of 2x. We don't get a nice ordered pair out of this as far as, nice numbers, but we get a function out of this that if we double the x's, this is what happens to the y's, is what we get out of that. Okay. Say we had f of x. Let's use the same function, 2x squared minus 3x. And they want us to find f of negative x. What does that do to our, what do we do with the negative x? I guess the best way to ask that. Put it in for x. So everywhere there's an x, put a negative x. What's that really got in front of it? It's like a negative 1 in front of there. So you just treat it like it's negative 1 and work it the same way we did example H. When you square negative 1, what's it turn into? Positive 1x, right? Or why is 1x squared? And then negative 3 times negative x would be positive 3x. So I'm going to go ahead and multiply this together and get 2x squared plus 3x. So if we change the sign of the x values, excuse me, then this is what happens to the y values. Okay? If we're just doing some algebra here, getting your brain going with some algebra skills that you should be fairly comfortable with. Maybe not. I hadn't done it in a couple of days, but not anything crazy. Here's an easy one that sometimes gives some people some problems. F of x is equal to 2x squared minus 3x. And they want us to find negative f of x. It's a really easy problem, but it always gives students problems. What does negative f of x mean? Not divide it, but multiply it. Get you the same answer, but yeah. So negative f of x, you're not changing what's in the place of x because it's just x in there, but you're taking everything and multiplying it by negative 1. Or changing the sign of everything. Negative 2x squared plus 3x. That's negative f of x. Really simple idea, but it seems like every semester it always gives some folks some issues. So kind of in the same line of things, if you had f of x is equal to 2x squared minus 3x, and they wanted you to find 3 f of x. What would that mean, do? Multiply everything by 3. That's right, Sabrina. Good job. So I'm taking 3 times 2x squared minus 3x. That's going to give me 6x squared minus 9x. And there's my function now. Nothing just incredibly difficult there. Same function, 2x squared minus 3x, but then the funnest one of all, f of x plus 2. F of x plus 2 means do what? What are we plugging in the place of x? Okay. Now, what do we do next? Do the x plus 2 squared, right? Yeah, exponents comes first. So how do you square x plus 2? Yeah, multiply it by itself. And that's not x squared plus 4. What is it? X times x is x squared plus 4x plus 4. And then what's going on here? Yeah, I'm multiplying everything by negative 3. It's in parentheses. So negative 3x minus 6. And I need to distribute this 2 so that I can combine like terms at the end here. It's 2x squared plus 8x plus 8 minus 3x minus 6. Combine like terms. So we got 2x squared. There's nobody else that's got an x squared. There's 8x and minus 3x, which would be what? 5x. 8 and minus 6. 2. All right. Nothing just too complex about that. Just some Algebra 1, Algebra 2 stuff kind of coming back. Got to make sure we remember how to do that sort of thing to get going there. I'm going to show you how to do this with the calculator. I want to show you that. I know some of you don't have yours with you today. Some of you do. But it'll be on video, and I can show it again tomorrow. It's not a problem. But I'm going to show you how to do a function value with the TI-84 Plus. Let's say they gave you this function, f of x is equal to 3x squared minus 5x plus 7. A couple of different ways to do it. Both get you the exact same answer. But I like to do, if I'm just getting one function value, I'd actually rather do it in the regular calculator screen. That way, if I need a fraction answer, I can get a fraction answer. If I need a decimal answer, I can get a decimal answer. If I use the y equals menu, which you may have done in Algebra 2, or you should have done in Algebra 2 some, then you're stuck with whatever format you're in. But if you do it in the regular calculator screen, it actually you can get any form of that. So if we've got this function and we want to find f of 1.25, so we got a decimal to plug in there, and so normally I would do things by hand, but here I'm going to do it with the calculator. I'm going to do 3 parentheses 1.25, close those parentheses, and then I need to square that. So I hit the squared button. Plus 5. Oh, no, that's minus 5, sorry. parentheses 1.25 plus 7. And then I just hit enter. And I get this decimal form of that, which maybe that's what I need. What if they ask you for it in fraction form? I can still get that from this screen. I'm going to go ahead and make sure I typed everything in right. 3, 1.25 squared, 5 times 1.25 plus 7. Yeah. 5.436. Okay. Or I could get that as a fraction by hitting math and enter twice. And 87/16. If I needed it in a fraction form. There are times you do, there are times you don't. It's just, being able to get either of those forms is important to be able to do. If I ask you to find, f of 26.07, that's a fun one. It's taking the same idea, 3 parentheses 26.07 squared minus 5 parentheses 26.07 plus 7. 1915.5847. I could get that as a fraction if I wanted to. Math, enter. And it says it can't convert it. I guess there's too many digits there to convert over to decimal from that decimal to a fraction. It won't. Basically 5,874 and 47. Sorry, dyslexia kicking in there. Over 10,000 doesn't reduce, so that it's not going. Can't get it to fit into its memory bank there. So stuck with that as a decimal there, which is okay. Normally, if you get a decimal at the beginning in my class, you're going to have a decimal at the end. Normally, folks that have had me before kind of know that. All right. So there's function value and function notation, using that sort of stuff to get some things done, and using the calculator to get there. Let's get into also in this section. First section is a little long, but doable. Let's go ahead and get into the funner part, if funner is a word, the domain of a function. This is an important part because we will do domain of functions the rest of the semester. Anytime we talk about any kind of functions in here, chapter 3, chapter 4, chapter 5, chapter 6, 8, in chapter 12 is like the only one we don't talk about function domain much in, but we do domain in every section other than chapter 12. Okay, so domain of a function. Domain relates to what? X values. So it's the X values that work for a function. Okay, when you're starting domain, every function has a domain that starts with all real numbers. You've heard that before? The term all real numbers you've heard before. We're going to start learning this thing called interval notation. When you start dealing with interval notation, we're going to do set notation and interval notation as we go through here. You got to be able to do both. As we kind of progress through the course, we bounce back and forth between which form you're going to need, and I'll tell you which one to use from time to time. The interval notation for all real numbers is negative infinity to positive infinity. Those are infinity symbols there. Okay. Negative infinity to positive infinity. Okay. Normally, if it's y equals 3x minus 2, like we had earlier, that function it has a domain of all real numbers from negative infinity to positive infinity. But there are some red flags that come up that will change the domain of a function based on really only two red flags that you've got to remember, okay? The red flags that we're going to look for. The first one is x's in the denominator. If there are x's in the denominator, what's the only number that we can never divide by? It's not a defined operation if we have 0 in the bottom. Right? Remember when we did slope in Algebra 1 or in 7th grade math, they do slope now. If it's 0 under the line, it's called undefined because you can't divide by 0. By definition, dividing by 0 is not possible. You can't take a candy bar and divide it between 0 friends, right? And you have to be dividing by into a number. So if there are x's in the denominator of the function, then that creates a division by 0 problem. And we got to figure out what's going on. Okay, so we'll work with some problems that have that going on. So that's the first red flag. You're going to look and see, are there any x's in the denominator of the function when they give us a function? And if there are, we're going to do some work to figure that out. What would cause the problem in this particular function? Okay. The other red flag that we have to look out for is square roots. When you took square roots in Algebra 2, what kind of problem made the square root weird? Or what kind of number made the square root weird? Not odd numbers. 25 is is an odd number. What made imaginary numbers? Square root of negative numbers. Negative numbers underneath there cause problems. So when we're talking about the domain of a function, we're talking about the x values. Imaginary numbers or complex numbers don't show up on a graph on a real coordinate plane. So if there are square roots in the problem, then those issues that could have go away if you look at positive only. Okay, so what we're going to be looking at is how do we figure out what makes it positive only if it's a square root? How do we figure out what makes it division by 0? So we're going to look at some problems and see if we can find the domain. And if there are red flags, we address them, and that changes our domain. If there are no red flags, what's the domain? If there are no red flags, all real numbers, negative infinity to positive infinity. If there are no red flags, that's the domain. If there are red flags, then we got to do something about it. Okay, and that's when we got to work on some stuff. So let's look at some problems and see if we can find the domain of those. Not doing anything else with them other than just finding the domain. Okay, what letter are we on here? All right. Our job is to find the domain. Here's our function. F of x is equal to x squared plus 5x minus 7. Well, we look at that thing, we look for those red flags. Are there any red flags in that particular equation? Are there any x's in a denominator? Can't be. There's not even any fractions in it. Hey, we don't have to worry about that red flag. Nothing doing there. Are there any square roots? Yeah. There's a square root there? All I see is a square, which is not a square root. Okay? So that's not a red flag. No red flags for something being squared, only if it's a square root. So there's no red flags here. So I'm saying there's no red flags. So that means our domain is, here's our notations. In set notation, curly brace with an X, and then a bar, straight up and down bar is what that is. Not the number one, it's just a bar. And then you put all real numbers. That's set notation. Interval notation, if there are no red flags, all real numbers is the domain. It's from negative infinity to positive infinity. Okay. That's what we're looking for. We're going to do both notations today, or today and tomorrow. We'll probably kind of bounce back and forth between the two from time to time. Okay, so no red flags, it's all real numbers. Okay, that's nice. Q of x. 5x over x plus 3. Let me rewrite that a little bit better. Okay. 5x over x plus 3. There's an x in the denominator. There's a red flag. Right there. That's a red flag because that x is in the denominator. So if an x is in the denominator, we need to know what number is going to make the denominator equal to 0. Okay? So what we're going to do is we're going to set x plus 3 equal to 0. Okay? And solve it. So whatever, if there's an x in the denominator, set the denominator equal to 0. Numerator, doesn't even matter. He's not doing anything wrong. Okay? So don't bother him. Okay? This guy's the one that's going to cause problems. Okay? So set that denominator equal to 0 and solve it. Easy math here. X equals -3. What that tells us is that's the value that's going to mess this problem up. If x is -3, then we end up with division by 0, and that's a problem. So that means x cannot be -3. X cannot be -3. All right? So for our domain, set notation is a little easier on this particular one. You have an x, and there's that bar again. X and a bar. That's how set notation is always going to start that way. Curly brace, x, and a bar. And then all you've got to do for set notation is tell them, hey, x can't be -3. Interval notation, a little bit more difficult. The way interval notation works is you're starting from negative infinity to positive infinity. That's where you're starting. So if we think about a number line, negative infinity is down here, positive infinity is up there. What number are we taking out of the game? -3. So we're taking number -3 out. So we're going to put this big empty spot where -3 is. Okay. So with interval notation, you've got all these numbers that are from negative infinity all the way up to -3. So we got to take care. We got to say, okay, from negative infinity to -3, it's all good. Everything's good as long as it's not -3. So we're going to put a parenthesis there on the -3. So it looks like an ordered pair, but it's an interval notation. So we're saying everything's good from negative infinity until we get to -3, and then we got to jump over -3. And the way we jump over -3 is we stop our interval, put a parenthesis, saying -3 is where we're stopping. Right before we get to -3, we're going to stop there. And then we're going to jump over that. And we're going to put a union symbol, which is just a big U. That means union. That means you hop over the -3 and you start right after -3. And everything's good all the way up to positive infinity again. So positive infinity right there. So interval notation, whatever your number is that you're throwing out, you've got to jump over it. And the way you jump over it is you go from negative infinity up to that number, parenthesis, union, start with that number again, go to positive infinity. What that tells us is we're doing every number that goes to -3 except for -3. Jump it, and then go all the way up to positive infinity. Okay. You'll get the hang of this. It takes a little practice with interval notation. Before long, you'll be like, oh, interval notation is nothing. That's the easiest part. Getting the answer is the hard part. Let's say we had this function. H of x is equal to 12 over x squared minus 16. Remember a little bit of algebra here. Is there a red flag for this problem? X in the denominator again. So we got a problem. We got to address it. What do we do to address that problem? Set what equal to 0? The denominator, x squared minus 16 equals 0. How do you want to solve that? There's a couple of different ways. Several different ways. I don't care which way you solve it. You can get x squared by itself. That works for this one. So that's x squared equals 16. And then what would you do? Take the square root, right? And if I take the square root of 16, what do I have to put in front of it? Plus or minus. Don't forget that. That's the part most folks forget when they're doing solving by square roots. Again, something that you've done in Algebra 1 or 2. Now, what's the square root of 16? So we have plus or minus 4. So x can't be those. X can't be positive 4. X can't be negative 4. There are two numbers we're carving out here. Okay? So when we write our domain, again, set notation for this particular problem is easier. X such that x does not equal plus or minus 4. There's set notation. Interval, a little bit more difficult. Okay, so with interval, we're starting at negative infinity and going up to what number? What's the first one we run into? Negative 4. So if we're starting at negative infinity, sometimes it helps to visualize that number line. We're starting at negative infinity. We're walking this way. We run into negative 4. That's a problem. Got to jump over that. How do we jump over negative 4? Negative 4, parenthesis, what goes next? U, negative 4, and then we're walking along, and what's the next number we come into contact with that messes things up? 4. We got to put a jump over the 4. So we stop at 4, pick back up at 4, and then we can walk on to positive infinity. So interval's a little bit more difficult on this particular problem because you got more things to cut out. But interval notation, I think, is much more descriptive in how it says what the domain is because it covers everything. This one just says, oh, x can't be plus or minus 4. But it doesn't tell you that all these other numbers are there. The interval notation, it does tell you all those numbers are there. That's our domain for that particular problem. Okay, so we're just looking for those red flags. Let's look at, we're getting short on time here, but we're almost done, so hang with me. F of x is equal to the square root of 2x minus 6. Ooh. Nice. Yeah. Or example donut, whichever one you call. Are we? Yeah. Are we? We are, aren't we? I'm a dummy. This is why my wife handles all the homework at home. Kids. I'll handle the math. All right. So what's the red flag that's going on here? Square root. Square root. All right. So if there's a square root, what kind of numbers are the only kind we want to take square roots of? Positive numbers. And what other number is easy to take the square root of? That's not really positive or negative. 0. 0 is also a positive. You can have 0 in a square root because we can take square root of 0. That works, okay? So what you want to do is take whatever's inside of the square root, that stuff there, and set it greater than or equal to 0. If you set it greater than or equal to 0, that means, okay, we're forcing this to be positive or 0, okay? Solve it the same way you would in an Algebra 1 class. Greater than or equal to 6. Don't forget the rules about if you divide or multiply by a negative that you got to flip the symbol around and all that fun stuff. All that stuff still applies. You don't have to do any of that on this problem. But it says that x is greater than or equal to 3. That's here when you're doing square roots is a little different because when we're doing denominator problems, that told you the numbers to throw out. The square root problems, this tells you the numbers to include. Okay, this tells you that x has to be greater than or equal to 3. Okay, the set notation is super easy for this. When you go to do your domain, the set notation, curly brace, x, and a bar, and then you just put that inequality there. X is greater than or equal to 3. That's super easy. The interval notation is really not that hard either, though. What's the smallest number that we are going to use here? 3, because everything's got to be 3 or bigger, right? So 3 is the first number. And then it goes up from there to positive infinity. Now, here's the difference. That's got an equal to mark. That means 3 is included. In the past, when we were cutting out the numbers, they weren't included, so we put parentheses. So to include the 3 right here, we need to put a square bracket. That means the 3 is included. So this says start with 3, it counts, and then go all the way to positive infinity, and that's the interval notation for that. Okay. It's going to take some practice, get used to interval notation and bouncing back and forth between set notation and interval notation. But it's doable and it's something we'll need to do as we go. I think I got the right letter this time. R. G of x is equal to the square root of 8 minus 2x plus 7. Okay. Got a red flag. Got a square root. Does that plus 7 that's hanging out on the outside have anything to do with the square root? No. So the only part that affects the domain is the square root part. That plus 7, it'll affect the range, but that really doesn't matter. We're not worried about that. All we're trying to do is find the domain of these functions. That's our job. Okay? So 8 minus 2x, what do we do with it to find the domain? Greater than or equal to 0. That's right. And then what? Yeah. So we subtract 8. Negative 2x is greater than or equal to negative 8. And then divide by negative 2. And what do I have to do if I divide by negative 2? Flip my symbol around so that x's are less than or equal to 4. Okay, so we had to flip that symbol because we divided by a negative. Don't forget that rule about solving inequalities. So let's get our domain. Again, set is super easy. X such that x is less than or equal to 4. Because it's just straight up what you got as an answer. The interval, a little bit more difficult this time because you got x is less than or equal to 4. So where are we starting at?
I need the following students to the office: Kylie Carroll, Selena McGee.
What's their smallest number? Negative infinity is their smallest number. And it goes all the way up to
seniors. From
4.
3 until 6 this afternoon, we will be having a FAFSA Frenzy event in the library. This is the last scheduled event before the January 16th deadline to fill out your FAFSA to be eligible for Tennessee Promise. Remember, you also must fill out the FAFSA in order to get the Hope Scholarship and any other form of federal or state financial aid. 3 until 6 in the AHS library, 2 days. Come and go, no appointment is necessary. If you have questions, come by my office today. And if you need to make an appointment for a different date individually, you need to have your parents contact me at the school.
All right.
Also, I need Gracie Hart to report to the office.
All right, we got through everything. So tomorrow, what your job is to come in and work on page 216. I'm suggesting 15 through 81, just the odd ones. If you have trouble, the idea is that you got the answers to the odd ones in the back of your book. I have my book in here that has the answers to all of them. If you have trouble with some of the odd ones, then you want to do the even ones that are close to them because they'll be very similar. And that way you can get more practice with the ones you need. Okay, so tomorrow we're coming in, we're working on page 216, 15 through 81, and we'll get our first work day in tomorrow. All right. Looking forward to a good semester with you kids. It's gonna be fun.